Yeah, number 3. Okay, so I thought I'd start by rewinding slightly. So I was about kind of halfway through this quantum cohomology of quiver varieties last time, so I'll just quickly rewind it. So just to recall the features of what's going on. So first of all, there's this Nakajima action by correspondences on the cohomology of a quiver variety. As I said, it goes back 30 years ago. And this was extended also, I don't know, probably also almost 30 years ago, extended by Varignolo to an action of this larger algebra called the Yangian, also by correspondences. Then we discussed that we have a description of the second cohomology, so which is like equal to the Picard group of the quiver variety using these tautological line bundles coming from determinants of tautological vector bundles. And this gives a map from Z to the number of vertices of the Dinkin diagram to this Picard group. And this map is almost always an isomorphism as long as we don't have some of the V's being 0. And we'll use this isomorphism to identify the second cohomology with the Cartan subalgebra of our Lie algebra. So this G was remember we started with the Dinkin diagram, and G was the semi-simple Lie algebra associated to that Dinkin diagram. And then I was in the middle, so this is where I was, basically where I left off. In the middle, maybe I'll stop here. In the middle of this theorem of Moloko-Kunkov. So the first part of the theorem says under this identification of the dual of the Cartan with H lower 2, this identifies the set of Kähler roots. So remember, this was defined in the general framework of quantum cohomology as those things which index the sum in the Kunkov conjectural description of quantum cohomology. Or equivalently, Q to this alphas will be the poles of the quantum multiplication. Those, okay? So, so that's what this delta plus on the left is, those Kähler roots. And the first part of the theorem says those Kähler roots coincide under this identification with just the usual positive roots of our semi-simple Lie algebra. So this, like, you should think is kind of a remarkable fact. I mean, the right-hand side is something just from Lie theory, and the left-hand side is something just from the geometry of quiver varieties. As a consequence of this fact, this parameter space for the quantum parameters, so this is where this Q's live, the parameters that appear in the quantum multiplication. They can be identified with this right-hand side, which is just the regular part of the maximal torus of G. So I'm calling the maximal torus of G H, capital H, because I'm already using capital T for this other torus, which is acting on the quiver variety. So this capital H, despite the weird notation, there's so many H's in this. This capital H is the maximal torus, or Cartan subgroup, of the group G. And H reg just means those elements in the maximal torus where the roots don't take the value 1. Okay. So that was the first part of the theorem. And the second part of the theorem was here, and this is exactly where I left off last time. So here we had this is this general Kunkov formula for quantum multiplication by divisors. So it's saying that in this case of the quiver varieties, finite type quiver varieties, ADE quiver varieties, the alphas here, this is, now we know that this sum is just over the usual positive roots. There's always this slightly mysterious thing, this Steinberg operator, that from the general framework we don't know what it is. It's sort of like a thing to be calculated. And the theorem of Moloko-Kunkov identifies it with the action of this very natural element of UG. This E alpha F alpha plus F alpha E alpha, where E alpha and F alpha are the usual root vectors of G. Okay, and then here was an example for SLM what those root vectors mean. So we've reduced the quantum multiplication by divisors to at least this part is purely expressed in terms of purely expressed in geometric representation theory. Purely expressed in terms of this action of G on the quiver variety. You might ask, can we do the same for this part, or can we do the same for the entire right-hand side? And the answer is yes, but we have to move outside of G and go to this Yangian. So that's somehow the next part. And I don't, this part I'm a little less specific about. I'll be more specific about this part when we go to the Afan-Grassmannian slices. But here's at least the statement. So the entire U star, U Q star, is the entire quantum multiplication by divisor. Oops, good, so there it is. You can basically fit it. So this entire thing, the entire right-hand side, is the image of an element of the Yangian. So we have this Yangian acting on the covariety. Technically, or not even technically, but an important point to note is that the Lie algebra or the Yangian, they don't act on the single covariety. They change your mu along the way because this Nakajima correspondence changes the gauge, changes the dimension vector of those gauge vertices. Okay, so the Nakajima correspondences, which is the action of the Lie algebra, moves you from one covariety to another, changing this mu. But if you look at just the weight 0 part of the Yangian, so this is weight in the sense of the usual weights of semi-simple Lie algebras. So for example, this guy has weight 0 because E alpha raises the weight and F alpha decreases the weight, so has weight 0. So if you look at the weight 0 part, we do get a map to there. Okay, so this part 3 of this theorem tells us that for any one of these UQ star guys, this quantum multiplication by a divisor is the image of an element of the Yangian, or more precisely, the weight 0 part of the Yangian. And not just like a element, but some element which has like a nice formula, which I'm not going to give. So these elements are called, they seem to have two names as far as I can tell in the literature. Sometimes they're called dynamical Hamiltonians, and sometimes they're called trigonometric Casimir Hamiltonians. Maybe the second name I made up, but certainly they're associated with this trigonometric Casimir words. Okay. So that's basically the main theorems of Molly-Konkov in the case of AD equivarieties. Any question? Yeah? Sorry, this map here? No, it won't be surjective. It won't be surjective. If you, again, it acts by correspondences. So it factors through, it's going to be a little messy, but let's just try. I think it factors through this. So you have this convolution algebra. Okay, so there's a convolution algebra sitting there. And unless I'm mistaken, it first of all, it factors, so it's not, and this right-hand arrow is not surjective. But I'm not, I think that this arrow probably is surjective, unless I'm mistaken. Yeah? Yeah, I mean, this is basically the quadratic Casimir of SL2 alpha, up to like a Cartan term. And actually, I think I've been a little bit lying throughout this whole thing. Like if you read Molly-Konkov, they always say plus, and then there may be some diagonal term. And I've been just like ignoring the diagonal term in my exposition, So like there could easily be a H alpha squared there, and you wouldn't have noticed it because I haven't been. I mean, like the Cartan acts just by these things are weight spaces. So on for any fixed quivariety, the Cartan just acts by a scalar. So if there was a extra term, it would just bring out a scalar multiplication by a scalar. So it's not very important. Yeah. How does it depend on Q? So they don't. That's somehow the point. The dependence on Q is entirely in this prefactor. Oh, sorry. This thing doesn't depend on Q. You're right. This guy, yeah, sorry. This guy will depend on Q. As I didn't give you a formula for it's hard to answer that question. But a little later, we'll have the analogous thing for affine Grassmannian slices, and you'll see the dependence on Q. But I mean, roughly speaking, the dependence on Q is it's going to be something. It's going to be something like this, which has like some Q's in it. So it depends on Q. Yes. Yeah. Yeah. So these elements depend on Q. Sorry. Okay. And now. So this was all about quantum multiplication by divisors, and you can ask now about quantum multiplication by higher degree elements of the quantum cohomology. And as I said, somehow less is known about this higher degree multiplications, and the literature is a bit vague about this topic. In all these papers of Akulkov and collaborators, they're always studying the quantum multiplication by divisors and not so much quantum multiplication by higher degree elements. But there is the following conjecture. So this is a conjecture that appears in Akulkov. I believe the conjecture is still open as far as I know. And it's proven in the case of cotangent bundle of partial Fag varieties, type A partial Fag varieties, in a nice paper by this series of authors, which came out around the same time as Akulkov. So these guys are Goburnov, Rymani, Tarasov, and Varchenko. Okay, so it tells us, the conjecture, that if we were interested in the entire quantum multiplication, so let's regard this, we're fixing a Q. Maybe I should write that at the beginning. So fix Q in this H reg. And then we have the entire quantum multiplication by all elements of the cohomology. And I think of that thing as a subalgebra of the endomorphism algebra. So all those quantum multiplications, they give us a subalgebra of the endomorphism algebra. A commutative subalgebra, because quantum multiplications commute with each other. And the conjecture says, on the other hand, we have a map from this Yangian to this endomorphism algebra. Again, technically the only degree 0 part of this Yangian, to this endomorphism algebra using this action of Arignolo. And there's a natural commutative subalgebra of the Yangian called a beta subalgebra. For reasons I don't know, Okunkov usually calls it the Baxter subalgebra. Other authors usually call it the beta subalgebra. I don't know what the reason why there are two names, but they both begin with B anyway. So there's this beta subalgebra in the Yangian, which depends on the same parameter Q. It's not actually that hard to define this algebra. I mean, it takes a little bit of theory of Yangians, but it's constructed using the R matrix of the Yangian. So there's this big natural commutative subalgebra depending on a parameter, same kind of parameter, inside the Yangian. And the conjecture says that if we take this subalgebra of the Yangian and use this map, I should write a map. So use this map here. Oh, okay, our map's already here. Use the map star star here. Then this beta subalgebra will be mapped exactly onto this quantum cohomology algebra, sitting inside this endomorphisms. And as I say, I believe this conjecture is still open. Any questions? Okay. Okay, so this wraps up the story of quiver varieties. So now we're going to go on to the parallel story of affine Grassmannian slices. Okay. So to get started on the story, we need some kind of geometric representation theory. So in the previous story, we got started by using this Nakajima and Varignolo results about actions of G and the Yangian of G on the cohomology of quiver varieties. And this time we're going to get started using the geometric Satake correspondence. So geometric Satake correspondence is like a great theorem, and I don't have time to really discuss it too much. But we're now going to involve two groups. So if you remember when we defined this affine Grassmannian, maybe I just better recall quickly the definition of the affine Grassmannian of a group. So remember we defined the affine Grassmannian of a group G to be G over the ring of Laurent polynomials divided by G over the ring of polynomials. And remember we gave a geometric description of this in terms of G bundles on P1 trivialized away from 0. And now there's this great geometric syntactic correspondence which studies the certain category of perverse sheaves on this Afan-Grassmannian and proves its equivalent to the category of representations of what's called the Langlands dual group. And today we're mostly interested, like in this lecture series, just talking about this simply laced case, in which case we can kind of ignore this Langlands duality. So occasionally I'll put some G-check around, but if you haven't heard of this Langlands dual group, you don't need to worry about it. You can just imagine that G-check and G are the same group. But what is important is that this geometric syntactic correspondence gives a relation between these subvarieties, Gur lambda bar in the Afan-Grassmannian, and these representations of the group G. So this is where the Langlands duality comes in the sense that this lambda was originally a co-weight, and on the other hand, EREPs we know are indexed by dominant weights. So we have to blur between co-weights and weights if we don't think about this Langlands duality. Okay. So so this word relation is a little vague. So relation, technical sense, means that there's this equivalence of categories, and the intersection cohomology sheaf on this Gur lambda bar is transferred to V lambda. But for our purposes, we're going to need the following. Okay. So let's continue as we did before. We fixed lambda, one of these dominant co-weights, and we assume it can be written as a sum of minuscule dominant co-weights. Okay, as I mentioned, in the case of SLM, every dominant co-weight can be written as a sum of minuscules, and in other types, there's less minuscules around, so not everyone can be written that way. But let's just assume we can write our dominant co-weight as a sum of minuscules. And then, as we did yesterday, I suppose, we formed this symplectic resolution. We took W lambda mu to be the intersection of Gur lambda with W mu, so this finite dimensional closed orbit closure, and this non-closed W mu. And Dinakar would prefer I put a bar here. Maybe he's right, but let's skip it. And then to make a resolution, we modify Gur lambda by replacing it with this convolution variety, which comes from this decomposition of lambda. So in terms of G bundles, let me just say it because it's probably the most intuitive way. So recall, Gur lambda bar means we put so remember we have G bundle, we have P and phi is an isomorphism trivialization away from 0. And this lambda, just to remind you, this lambda puts a condition on the poles of phi, and this mu puts a condition on the isomorphism type of P. And when I pass to this version of convolution, what I'm doing is rather than having one principal G bundle, a whole sequence of principal G bundles with isomorphisms between them away from 0. Okay. So we can make what I call the naive identification between this cohomology of the resolved Afan-Grassmannian slice and the right-hand side, which is the weight space in a tensor product representation. And the way we make this naive identification, it's not so bad. It's a good identification. It is compatible in some sense with geometric syntactic. But the way it works is the right-hand side has a natural basis. So each one of these representations are minuscule, which means they have a basically well-defined weight basis because all the weight spaces are one-dimensional. So each of them have a basis. So together we can form the tensor product basis. So on the right-hand side we have a natural tensor product basis. On the left-hand side there's also a natural basis, and it's called this notion called stable basis. So Maliko Kunkov introduced this stable envelope construction, and in this case the stable envelope is a map from basically from the cohomology of the fixed point set to the cohomology of your symplectic resolution. In this case, the fixed point set is just a bunch of points, so the stable envelope map gives you a basis. Okay, I don't have time to get into definition of stable envelope map and stable basis, but suffice it to say that you can define a naive identification by matching the stable basis with the tensor product basis. So I like okay, well, we'll come back to this in a second. So this is like level 1, and just like in the previous case, we had level 1, which was this Nakajima action, like level 2, which is this Yangian action. This is kind of going to be our level 1, and our level 2 will be the following. Okay, so this is a little bit more involved representation theory, so let me just work through it slowly. So first of all, there's this general construction. Given an element in the dual of the Cartan, you can always form a Verma module. So Verma module means you take the module freely generated by some vector of weight theta, which is a highest weight vector. So its action, the Cartan acts on the vector by the weight theta, and all of the upper triangular part of your Lie algebra annihilates the vector. In a formula, it's this. You take one-dimensional vector space with an action of this universal enveloping algebra of the Borel subalgebra, and then you tensor it up to give a representation of UG. So this is classical construction in representation theory of semi-simple Lie algebras, and gives you this thing called the Verma module. Okay, and so then here's like a weird trick. So say we have a finite dimensional representation V that we're interested in, and a weight mu. So we're interested in the weight space. So we have some finite dimensional representation V, might be irreducible, might not be irreducible. It's going to turn out, we're going to apply this for this tensor product representation. So we're interested in the mu weight space of the representation V. And so there's a weird trick. We're going to replace this weight space by the following strange thing. So you take V and you tensor it with a Verma. And then you look at Hom from a different Verma, now shifted by mu into that Verma, into that tensor product rather. And I claim this is pretty closely related to this weight space. Why? So if you're given something in the right-hand side, it maps you from, it gives you a map from here to here. So you can feed in this guy, V theta plus mu, that's my notation for the highest weight vector here. So I feed in, I take my phi, which lives on this side, it's a homomorphism. I feed in the highest weight vector, and it now lives in the right-hand side. So this guy is in the right-hand side. It's not just anything in the right-hand side. Because it came from this Verma, and because the map was G-equivariant, this thing is of weight theta plus mu. And moreover, it's a highest weight vector. It's annihilated by all the elements of the n plus. So this is a highest weight vector of weight theta plus mu. In fact, by the universal property of the Verma, this homomorphism space is the same as the highest weight vectors of weight theta plus mu. So you have this highest weight vectors of weight theta plus mu here, sitting in the right-hand side. And now every such vector sort of can be decomposed into this tensor product, and there'll be some part of it which in the theta side has weight exactly theta. And therefore, on the V side has weight exactly mu, because overall the weight is theta plus mu. So I can project onto the mu weight space of V using this operator. So this is like the dual of V theta tensor the identity. So this is, I don't know, some kind of standard construction in Lie theory, but that I needed to bring up. Okay, so if theta is generic, then this map's always an isomorphism. If theta is not generic, the map, I think, will be neither necessarily injective nor surjective. But when theta is generic, the map's an isomorphism. Okay. So the reason why I bring this up is because we're going to make use of this thing. So this result of Ginzburg-Riesz tells us the following. That if we're interested in the right-hand side, which we are interested in, cohomology of the Affine-Grassmannian slice, specialized. So a lot of the time in the next little bit, I'm going to specialize this equivariant parameters. And actually, I think it's never necessary. I could have not specialized it at the cost of, on the other side, writing a more complicated thing. So I would, instead of working with a specific Verma module, I have to work with a universal Verma module, and so on. So to avoid thinking about that, it's somehow psychologically better for me to specialize on the equivariant parameters. But it's, I think, never necessary in what I do. Okay, so here we have specialized equivariant cohomology. And on the left-hand side, we have precisely this construction, this replacement of V mu. So we were saying from the very beginning that this equivariant cohomology is pretty closely related to the mu weight space in this tensor product. By the way, from now on, I'm going to introduce this notation. So keep in mind, I'm using V with a lambda underline always means the tensor product, because there's going to be so much times that you need this tensor product of these fundamentals. So I just use V with lambda underline. So we were saying that this is equal to the mu weight space in this tensor product. And now I'm going to, using this idea, I'm going to change it and replace it with this Hom like so. And this result of Ginzburg-Rees actually tells us that we have a natural isomorphism like that. So it's a fine thing to do to rather work with this instead. Okay. But for like generic theta, they're the same. I mean, this is the same. The left-hand side is the same as that weight space. Okay. So now we need one more piece of notation before stating the main theorem. So the notation is the following. This thing might be familiar to you or might not be, but let me explain slowly then. So any semi-simple Lie algebra has a natural Casimir element. Casimir element means we pick a semi-simple Lie algebra has up to scalars. Well, if it's simple at least. If it's simple Lie algebra has up to scalars a unique invariant bilinear form, which you could choose to be the killing form. And associated to that bilinear form, there's a Casimir element. I mean, associated to a bilinear form, invariant, associated to a non-degenerate bilinear form in any vector space, there's a Casimir element. But in particular, on this semi-simple Lie algebra, we have this Casimir element. So it's just obtained by taking a basis and a dual basis and taking the basis tensor the dual basis and summing. So that's omega. It lives in G tensor G. And now I'm going to make an element omega ij, and I and j are just two indices, which lives in UG tensor n rather than in G tensor G. And how do I do it? I just insert the Casimir in those I and j tensor factors. So in a formula, there it is. It's like a little hard to read. But there's like ones everywhere except in the I and j tensor factor, and I put a basis in the dual basis, and I sum over k. So these are some nice elements inside of UG tensor n. Maybe for now, one reason why they're nice is because they commute with the diagonal G that's sitting inside of UG tensor n. Basically, because the Casimir is G invariant, they'll commute with this diagonal G for any I and j. Okay, they're just needed to state the theorem. Okay, and oh, whoops, one more definition before we get to the theorem. So the definition of these things called Gaudin Hamiltonians. So what is it? So there are certain linear combinations of these omega ij's. So more precisely, so I take n distinct complex numbers, and I define the Gaudin Hamiltonian to be a linear combination of those omega ij's, where the coefficients are 1 over zi minus zj. So it's important, of course, that these z1 through zn are distinct, so this denominator doesn't vanish. And I call this linear combination a Gaudin Hamiltonian. So what makes these guys so nice is that they commute among each other. So it's not very obvious from the formula that they should commute among each other, but they do. So for a fixed z, these n different guys commute among each other. Their sum is 0, so they only span an n-1 dimensional subspace, but they do span an n-1 dimensional commutative subspace of UG tensor n. So they're going to play actually a fairly big role in what follows, especially in the next couple lectures, so maybe it's worth taking a look at their definition. For those people who are familiar with the Kamnitze-Zamolodchikov connection, which might be nobody, but you might have seen these things. They're exactly what appears in the definition of the Kamnitze-Zamolodchikov connection. Okay. Okay, so we need one more ingredient, before stating the main theorem now. So the remaining ingredient concerns as we did before with covarieties, concerns an analysis of the H2. So we begin with the following thing. So this resolved affine-Grassmannian slice sits inside n copies of the product of n copies of the affine-Grassmannian, because it's like a sequence of points in the affine-Grassmannian, which are related to each other by this lambdas. So it sits inside of n copies of the affine-Grassmannian. The H2 of the affine-Grassmannian is isomorphic to Z. Again, I guess probably I'm assuming that G is simple. Is isomorphic to Z. And so this inclusion, we get a map backwards on cohomology. So we get a map from Z to the N to the second cohomology. And it's not that hard to see that it factors through Zn mod Z times the all ones vector. Basically, the reason is because on this W mu locus, so which kind of thinks, on W mu, the standard line bundle in the affine-Grassmannian trivializes. So that's why we get this factoring. And this arrow here is usually an isomorphism. I didn't try to look up exactly when it's not an isomorphism, but it's something like, again, as we saw before in the quiver variety case, it's something like almost always, like it would be something very degenerate would be happening if it wasn't isomorphism. So to understand this a little better, let's look at an example. So let's pass the GLM. And I mentioned before, you can think of these affine-Grassmannians for GLM as being about space of lattices. And so in particular, we can think of the following thing. So we have this convolution variety. So we have lambda with an underline. And this lambda, maybe I should be a little more precise. So this lambda with an underline, it's a sequence of fundamental weights of GLM or SLM. And every fundamental weight is like omega k, where k is between 1 and m. So I can write this lambda underline as omega k1 up to omega km. N, sorry. Where these numbers ki are between 1 and m minus 1. And then this corresponding convolution space, well, let me ignore the mu for a second, but the corresponding convolution space will be a decreasing chain of lattices, L1 and so on up to Ln, where the jumps, the k's indicate how much the lattice jumps. So these are all infinite dimensional vector spaces over C, but the quotients that you get this way are all finite dimensional. So these are finite, the quotients here are finite dimensional over C. So each one is finite codimension in the previous one, where the codimension is given by the k, which is appearing in this lambda. And then there's an additional condition, which is related to the, well, because we're in this, working in this fundamental thing, then we get this condition of how this t operator, which comes from multiplication by t over here, how it interacts with these lattices. And finally, there's a condition related to mu, which is mu just imposes a condition on the last lattice, which is just that Ln is in W. Okay? From this perspective, we have natural line bundles. These tautological, well, we have tautological vector bundles coming from quotients. So this is like a flag-like space. So we take quotients, we get tautological vector bundles, and we take determinants of those things, and we get tautological line bundles. Then we take the first Chern class, and we call that thing dj. So these, this dj is going to be exactly the basis of this H2 here. And these generate this Picard group. But there's a fact that if you take the first lattice, divide it by the last lattice, because of this condition, which I didn't really tell you about how to translate in terms of lattices, it implies that this determinant of this quotient is actually trivial. And so this determinant of this quotient being trivial, that's a manifestation of the fact that it factors through this. So that rather than these dj's freely generating the Picard group, there's a relation that the sum of the d's is 0. So it becomes d1 plus dn equals 0. Okay, so this is a description of the H2, or Picard group, of the affine-Grassmannian slice. Resolved affine-Grassmannian slice. So we need like to use this description in order to state the theorem about the quantum cohomology. That's why it's coming here. Any question? Okay, great. And now we're ready for the theorem, which is basically due to Danilenko. Okay, so just like the theorem I started with today, which was Molykov-Krukhov's theorem, the basic point is to understand this this standard description of the quantum multiplication by a divisor in this example. Okay, so the first step is to identify the Kähler roots. So to identify the Kähler roots live in H2, lower 2, with coefficients in Z. So under this identification of H upper 2, well, we get a dual identification of H lower 2. And so dual to Zn mod Z times all 1's vector is the set of all A1, AN, which add up to 0. So if you like, this is like the weight lattice of SLN. This is like the root lattice of SLN, or the first thing is like the weight lattice of SLN. The second thing is like the weight lattice of PGLN. However you like to think about it. So this H lower 2 is identified with the space of all n tuples of integers, which add up to 0. And under that identification, this set of Kähler roots, which again is completely determined just from the geometry, from the quantum multiplication, is identified with the set of the roots of the AN Dynkin diagram. AN minus 1 Dynkin diagram. So this epsilon I minus epsilon j. So you put a 1 and you put a minus 1 somewhere in your n integers, okay? Where I is less than j. And of interest is that like this is independent of what type, there's a group G floating around, but the group G doesn't influence the roots at all. The roots is only influenced by n. And what is n? N is just like the length of the sequence lambda. So this set of roots and this whole business here, all this stuff here, only depends on n, which only has to do with the length of lambda. It's kind of universal for every affine Grassmannian slice, where the length of the lambda sequence is n. Okay, so that's the first part of the theorem. Second part of the theorem, we need to identify the quantum multiplication by divisor. And as in the Molykov-Krukov theorem, like the first step is to just identify what those operators are. So we're supposed to have one operator for each root. This L operator, one for each root. So here's the theorem. So it tells us quantum multiplication by divisor equals classic multiplication plus H times this pairing of U with the root times this Q factor times, now what's the L? Here's the theorem that the L is precisely the action of that omega ij guy. So what's omega ij? Now that it appeared, we better remind ourselves what it was. It was take the Casimir and insert it in the ij tensor factors. And how does that thing act? Let's go back. How does that thing act? So here we use this naive identification. So identify the cohomology of the affine Grassmannian slice, resolve the affine Grassmannian slice with the weight space of the representation, maybe tensor the covariant cohomology point. And it's again this naive identification by matching the tensor product basis with the stable basis. So we match tensor product basis with the stable basis, and once we do that, the action of those L alphas, those things appearing in the right-hand side of the Okonkov formula, become the action of those omega ij's. Those guys act over here, right? So this omega ij, it lives in UG tensor n, so it's well defined and acting over here. So, okay, so this is the second part of the theorem. So this is exactly analogous to what we saw in the quiver variety story, where we had the action of those E alpha, F alpha plus F alpha, E alpha. Now we have an action of a different kind of quadratic thing now living in UG tensor n, these omegas inserted in the ij spot. Okay, a question? Yeah?
But why do we need the nth tensor power of the enveloping algebra to argue that means? Ground frequency does the corresponding element in this UG and put it there?
So so on this, so this vector space appearing here is a tensor product. By definition, it's this v lambda. So I'm using my this convention from now on that v lambda underline means v lambda 1 tensor v lambda n. So on one hand, you could say, okay, it's a tensor product, but therefore it's a representation of G. So you could say, well, can't I just find some element in UG and use that element to act there? But it's just not true. It can't be expressed as something coming from the action of UG. You need to think of it as a representation of UG tensor n. You need to use all the freedom you have. You can't just like think of it as just a G representation. Yeah?
One point is using this identification. Is it possible to construct some cohomology algebra directly on the resolved
yeah, so this is a very good question. So let me whoa, it's a good question. We'll take a little bit of effort to answer this question. Okay, let me try. So roughly, I think the answer to your question is the following. So if we take if we consider the endomorphisms as a G representation, let me drop the mu for a second. It's going to make things more confusing. Drop the mu for a second. So if we take the endomorphisms of G as a endomorphism of V lambda, but regard it as a representation of G, so as a tensor product representation. On the one hand, this will have a surjective map from the elements of UG tensor n, which commute with the which commute with the diagonal G. So like UG tensor n acts on this V lambda, this tensor product representation, and some elements of UG tensor n commute with the diagonal G. And for example, like all of my omega guys live here. Those guys will commute with this diagonal G. And so you, and it turns out that map's surjective, okay? On the other hand, via the geometric Satake correspondence, you can realize this thing as something like a convolution algebra, H top of this Gur lambda tilde guy. So let me write, I'm just saving a little notation. It says Gur lambda with an underline means that convolution variety cross over the affine Grassmannian with Gur lambda. So, and then you could intersect that thing with W mu and get the convolution variety for the affine Grassmannian slice. So yes, all these omega ij's can be thought of as living inside of such convolution varieties, which they should be because of that Okunkov, basic Okunkov conjecture that this L alphas all come from convolution. So yes, they do come from convolution. On the other hand, I don't know any explicit description of omega ij as a particular cycle on the right-hand side. Like in general, it's going to be some kind of linear combination of cycles. So somehow, in the work I did almost, 15 years ago or something with Savinkadis, was a little bit about this kind of topic. And it's like not so straightforward to realize those omega ij's or any other things you might be interested in as explicit, understanding exactly what correspondences they correspond to. In a similar way, when we go back to that theorem from before about the quantum cohomology of quiver varieties, I said, okay, the L alpha is this E alpha F alpha plus F alpha E alpha. And you could ask, what correspondence does that correspond to? So when you have a simple root, then Nakajima describes what correspondence to use for a simple root. But for an arbitrary positive root, I don't think there's not a simple description of what correspondence. It's going to be some linear combination of things. So in a similar way, this thing will be a little bit complicated. Any other questions?
In that example, the Cato roots together with their negative form a root system. Is that always the case for any symplectic solution?
It's a very good question. Also, in the previous example, they also form a root system. Is there any general theorem, expectation like that? I don't think in general they're going to form a root system. For the hypertoric varieties, I'm looking at Jeremy. Did the set of Kähler roots and their negatives form a root system always? Say in the case of hypertoric varieties.
They form something more generalized.
Yeah. Okay, not always a root system. Okay, any other questions? Okay. I should say as an advertisement for Jeremy's talks, if you like these talks, then Jeremy's going to sort of, well, in a very short amount of time, going to do the hypertoric variety version of this talk. Okay. Now, third step. Just like before, in the equivariety case, we might want to describe not just like this like nice, whoops, just this, not just this like terms that are appearing here, but maybe this entire quantum multiplication in some way. So how can we describe this entire quantum multiplication in some way? And for that, we need somehow, in the previous case, we needed to use this Yangians, and now we need to use this like more sophisticated identification. So what I mean by that, we have this Ginzburg-Riesch identification as follows, that I mentioned earlier. And we have those divisors, di. So di is like the divisors I explained about coming from the ith copy, the embedding of this into the ith copy of that Finger's mining. So we have some natural divisors here. And on the other hand, we have those Gaudin Hamiltonians, HIs, which I defined a few minutes ago, which are certain linear combinations of these omegas. But I'm going to look now slightly, so this is where things get slightly confusing. I take Q. So what's Q? Q is a quantum parameter. It lives in that torus, the regular part of the torus, which in this case is just the torus C star to the n, mod C star. And then the regular part means I throw away this delta. So this throwing away the delta corresponds to the fact that I want this Q. Remember, what I need to throw away is where Q to the alpha is 1. And Q to the alpha, I should write it somewhere. So this means that Q to the, this epsilon I minus epsilon j thing is just Qi, Qj inverse. So if I delete the locus where Q to the alpha is 1, that's the same as saying Qi is not equal to Qj. So that means this delta means the distinct endpoints in C star. So this Q parameter, quantum parameter, is n distinct complex numbers, n distinct non-zero complex numbers, modulo simultaneous scaling. And now I feed those into my Gaudin Hamiltonian, but I also add a 0, and thereby obtain an element in UG tensor with itself n plus 1 times. So I just remind you, or maybe rewrite it. Oh, maybe I'll remind you. So this is some linear combination like so. So now here I had n numbers, but now I've made myself n plus 1 numbers by adding a 0 sort of to my q's. So this list of numbers will be n plus 1 numbers with 0 and then the q's. And I use those guys to make a linear combination of these omegas, which will now live in tensor product n plus 1 times. So this Gaudin Hamiltonian living in tensor product n plus 1 times, this will act on this Hom space. Because here I have n plus 1 tensor factors. 1 tensor factor here and n tensor factors here. 1 tensor factor here and n tensor factors here. So this Gaudin Hamiltonian, it likes to act on thing with n plus 1 tensor factors, so it will act there. It will act there, and it will commute with the diagonal G action, because it commutes at the diagonal G action, it acts on any Hom space of any G representation in there. So it acts on this funny version of V lambda mu. So remember, this whole thing on the right-hand side was a funny version of this tensor product multiplicity space. And so under this Ginzburg-Riesz identification, the action of quantum multiplication by divisor becomes the action of this Gaudin Hamiltonian. So this is the analog of what I said like half an hour ago about quiver varieties, where I said that the action of quantum multiplication by divisor on the quiver variety is this dynamical Hamiltonian, and I didn't define dynamical Hamiltonian, but now I'm able to do it in this Afran-Grassmannian slice case to define this Gaudin Hamiltonian acting in a kind of funny way via this Ginzburg-Riesz business. Okay. Just check the time. Okay, we have 10 minutes left. Okay, so perfect. So if you don't like this funny business on the right-hand side, you can avoid it. And in fact, if you look at Danilenko's paper, which I'm mentioning, he doesn't actually do this. This 3 doesn't appear sort of in his work. He does something a little different. So you can avoid it at the cost of writing a more complicated formula. So maybe I won't get into what this more complicated formula is. But the main point is that I've swapped out n plus 1 for n. Okay, so rather than this thing, which is maybe not such a bad formula, but it involves n plus 1 tensor factors, then you have to do this funny business here. Here, we just have n tensor factors, and we can act directly on this v lambda. And we can form this thing, which we call trigonometric Gaudin Hamiltonian. So it's a bit more complicated than the usual thing. In particular, there's this bit here, which I don't want to bother explaining. Okay. And then the version like of 3, you can, instead of this 3, you can replace it with what I'll call 3 prime, which tells us simply that the action of this quantum multiplication by a divisor is given by this trigonometric Gaudin Hamiltonian. So just the action of this trigonometric Gaudin Hamiltonian on the weight space in the tensor product, no funny business needed. And I should say that like 3 and 3 prime are not exactly equivalent. Only like, because you can only exactly transfer from here to here for generic theta. And so if you look actually what Danilenko proved, he proved 3 prime for generic theta. And oops, so here's a little comment. So actually what appears in this work of Danilenko is not 3, but 3 prime, and only for generic theta. And in our work, so this is a recent paper from last year with Eccellenza and Leonid Rybnikov, who's arriving very soon in Pisa. We proved the equivalence of 3 and 3 prime for generic theta. So technically, this theorem that I mentioned is not quite, if we look back at this statement of the theorem. So if we think of part 3 of the theorem, I would say it's only proven for generic theta, and I would say it's conjectural for arbitrary theta. So, I think it's potentially an interesting problem is to extend this Danilenko to arbitrary theta. So again, for generic theta, 3 and 3 prime are equivalent, and 3 prime is what Danilenko proved, but only for generic theta. So I suspect that for generic theta, 3 is the right answer, not 3 prime. For arbitrary theta, 3 is the right answer, not 3 prime. Okay, any question about this slightly technical point? Yeah. Yeah.
What's trigonometric?
I never understood the answer of that. Maybe we can try to introduce some trigonometry later into the story. Yeah? Yeah? Is that a question or a comment? I think something like that, yeah. So in a little bit, we're maybe next lecture, we're going to consider some other versions of this. Maybe we'll, the question will be more answered then. Yeah?
What are you trying to avoid if you wanted to use this formula over the one with the modules?
Well, Nothing, I mean, well, for one thing, this is the one that Danilenko proved, not this one. So that's the first thing I should say. So Danilenko didn't prove 3, he proved 3 prime. So, and secondly, I don't know, this identification is a little more complicated because as I mentioned, the naive identification, which is what Danilenko used, just matched the stable basis with the tensor product basis. And maybe I should have said this a long time ago, but well, it couldn't have been that long ago, but in the past, yesterday I could have said it maybe, that in this method of Okunkov and collaborators, like all those long lists of papers, usually, not always, but the main method they use is doing computations in the stable basis. So that's like the bread and butter approach is to compute this quantum multiplication in the stable basis. And thus, matching the stable basis with this tensor product basis is like very helpful. So they just match it and then do the computation and see you get the action of this thing on the tensor product basis. Okay, any other question? If not, then we have just enough time for my little, oops, sorry, not enough time. Okay, quickly. Maybe we'll get back to this a little later, but so there are those Gaudin Hamiltonians, and they can be embedded in a much larger commutative algebra called the Gaudin algebra. So depending on the same parameter, so we have this parameter z, and remember those guys, those funny linear combinations of those inserting the Casimirs, and there's a bigger commutative algebra which still commutes with the diagonal G, which is called the Gaudin algebra, defined in this fairly classical work now of Fagan, Frankel, Rishtikin from 25 years ago maybe. And it uses the center of the affine Lie algebra at a critical level. And so that brings us to the following conjecture, which, well, I never saw it exactly in print before, so we can say this formulating it here for the first time precisely. So under this isomorphism, under this Verma module identification, the action of this Gaudin algebra is the same as the action of all quantum multiplication by any elements. And as I said, like the main evidence for the conjecture is that on the left-hand side contains these Gaudin Hamiltonians, and we already know that those Gaudin Hamiltonians match the multiplication by divisors, and this is a natural way of like increasing the size on both sides, so it seems reasonable conjecture. And it's supposed to be parallel. Well, okay, so now comes the final summary chart. Okay, so this, well, okay, good. Maybe just enough time to present this chart. So let me just recall what we've done. We started with the data of, say, a simply Lie semi-simple Lie algebra, 2 dominant weights, and the lambda we wrote as a sum of minuscules. And then we have 2 varieties, 2 symplectic resolutions, the curve variety and the resolved affine Grassmannian slice. And we wanted to study how the quantum multiplication by divisors works in these 2 varieties. So we have this basic Okunkov formula for quantum multiplication by divisors, which is controlled by 2 things. One is delta plus, and one is this L alpha. So we've seen now today that how everything works on both sides. So for example, the Kähler roots, this delta plus, are just the usual positive roots. Whereas in the curve variety side, whereas in the affine Grassmannian side, it's the roots of the an-1 root system, independent of G and only depending on n. We've seen that on the curve variety side, those L alphas, which are called Steinberg operators in the Okunkov story, are given by this E alpha, F alpha plus F alpha, E alpha, whereas in the affine Grassmannian slice, those L alphas are given by omega ij's. We've seen that you can also try to capture not just like this individual terms on the right-hand side, but this entire right-hand side. And when you try to capture the entire right-hand side, you need to do something a little more complicated. And on the curve variety side, that means you look at these special dynamical Hamiltonians in YG. And on the affine Grassmannian side, you look at those Gaudin Hamiltonians, but acting on the right-hand side via Ginzburg-Riesz. And finally, if you want to capture the entire quantum cohomology algebra on the curve variety side, last part is conjectural on both sides. if you want to capture the entire quantum cohomology algebra, you should look at these beta algebras inside of YG. And on the Affine-Grassmannian slice, you should look at these Gaudin algebras acting again via this Ginzburg-Riesz isomorphism. Okay, so I'll stop there.